Welcome to our exploration of conductometric titrations, a fascinating technique in physical chemistry. In this video, we'll break down what conductometric titrations are, why they're important, and how they work. Whether you're a student or just curious about chemistry, understanding this method will give you insights into how scientists measure and analyze chemical reactions using conductivity. Let's start by setting the stage for what you'll learn: the basic concept, the underlying theory, the experimental setup, and the practical advantages of this approach. Conductometric titrations are a special type of titration where the endpoint is determined by measuring the conductivity of the solution. Instead of relying on color changes or other indicators, this method uses the electrical conductance of ions in the solution to signal when the reaction is complete. This is especially useful for reactions where traditional indicators don't work well. By tracking how the conductivity changes as one solution is added to another, chemists can pinpoint the exact moment when the reaction reaches its equivalence point. Core principle of conductometric titrations is based on the variation of conductance during a chemical reaction. Conductance depends on the number and mobility of ions present in the solution. As the titration progresses, ions with different mobilities replace each other, causing measurable changes in conductivity. At the equivalence point, there's a sharp change in the conductivity, making it easy to determine the endpoint accurately. This principle is what makes conductometric titrations both reliable and versatile for a wide range of chemical analyses. Conductivity is a measure of how well a solution can conduct electricity, which depends on the type and number of ions present. In conductometric titrations, this property is key. As you add a titrant to the solution, the ions interact and change, altering the overall conductivity. For example, replacing highly mobile ions with less mobile ones will decrease conductivity, while the opposite will increase it. Monitoring these changes allows chemists to track the progress of the reaction in real time. To perform a conductometric titration, you'll need a few key pieces of equipment. The main setup includes a beaker containing the solution to be titrated, conductivity cell dipped into the solution, and a burette filled with the titrant. The conductivity cell is connected to a Wheatstone or conductivity bridge, which measures the solution's conductivity. As the titrant is gradually added, the conductivity is measured after each addition, and the results are plotted to find the equivalence point. Instruments used in conductometric titrations are designed for precision. The conductivity cell is sensitive to changes in ion concentration, while the Wheatstone or conductivity bridge provides accurate readings. The burette allows for controlled addition of the titrant. Together, these instruments ensure that the titration process is both accurate and repeatable, making it ideal for both educational and research settings. Procedure for conductometric titrations starts with measuring the initial conductivity of the solution. The titrant is then added in small increments, with conductivity measured after each addition. This process continues until the reaction is complete. The data collected is used to plot a graph of conductivity versus the volume of titrant added. The intersection point of the two lines on the graph indicates the equivalence point, which is the goal of the titration. One of the strengths of conductometric titrations is the graphical analysis. By plotting the conductivity against the volume of titrant added, two straight lines are typically observed. The point where these lines intersect marks the equivalence point. This graphical method provides a clear visual way to determine the endpoint, reducing the risk of human error and increasing the accuracy of the titration. Let's look at a classic example: titrating a strong acid like hydrochloric acid HCl with a strong base such as sodium hydroxide NaOH. As the base is added, the highly mobile hydrogen ions are replaced by sodium ions, leading to a distinct change in conductivity. The graph shows a sharp intersection at the equivalence point, making it easy to identify when the reaction is complete. In titrating a strong acid like HCl with a weak base such as ammonium hydroxide NH4OH, the conductivity changes differently. The replacement of hydrogen ions with less mobile ammonium ions results in a less pronounced change in conductivity. However, the equivalence point can still be determined accurately using the conductometric method, showcasing its versatility. In the case of titrating a weak acid like acetic acid CH3COOH with a strong base such as NaOH, the conductivity increases steadily as the base is added. The acetate ions formed are more mobile than the original ions, leading to a characteristic change in the graph. This example highlights how conductometric titrations can handle a variety of acid-base strengths. Titrating a weak acid like acetic acid with a weak base such as ammonium hydroxide presents a unique scenario. The conductivity changes are more subtle, but the conductometric method still allows for precise determination of the equivalence point. This demonstrates the method's effectiveness even when both reactants are weak. Here are some real images of conductometric titration setups and instruments. These visuals help you connect the theory to actual laboratory practice. Notice the arrangement of the beaker, conductivity cell, and burette, as well as the digital displays used for measurement. Such setups are common in academic and research labs. Let's take a closer look at additional images from the laboratory. These show different angles and setups, reinforcing the practical aspects of conductometric titrations. Observing these real-world examples can help you better understand how to set up and perform your own experiments. Conductometric titrations offer several advantages over traditional methods. They can be used for colored solutions where visual indicators fail, and they're effective for very dilute solutions in weak acids or bases. The graphical determination of the endpoint increases accuracy and reduces subjective errors. This makes conductometric titrations a preferred choice in many analytical scenarios. Summary: conductometric titrations are a powerful tool in physical chemistry, allowing for precise and reliable determination of reaction inputs. By measuring conductivity, chemists can analyze a wide range of reactions, even those that are challenging for traditional methods. The combination of theory, practical setup, and clear advantages makes this technique essential for students and professionals alike.